Hey, I had a question for the Zoom audience. Were you able to see my slides and can you hear me talk right now? Okay, I see a thumbs up. So so I'm just gonna share my screen. Just yell if you can't see my slides or anything at some point. Okay.
Very good. So welcome everybody to the New Technologies and Mathematics Seminar of the CNSF. Today we have Surya Ganguli from Stanford and also from AI research. So that's what actually started out in string theory, but saw Pruning and now is a leader in applying physics and many other techniques to problems of neuroscience, problems of machine learning. So he'll tell us about research on data pruning and scaling laws. So please.
Cool. Thanks, Michael. So yeah, it's always fun to come back to Harvard, and good to see some old friends. And yeah, so let's get started. And yeah, for the Zoom audience, if for any reason you can't hear me or see my slides, just yell and I can't see the Zoom window right now. All right. Okay, so in our lab, we do a bunch of neuroscience. We try to understand, how biological neural circuits work. These are some works that we've done on theory, experiments, and data analysis in neuroscience. But there's sort of a bigger problem that suggests a need for motivation or motivation for alliances between somewhat different fields: neuroscience, machine learning, physics, and mathematics. And this is the motivation, right? We're doing neuroscience. Oh, okay. You're not seeing the slides? Okay, let me go back to. Oh, I see. Got it. Okay, let me share the screen. Desktop.
Good.
Hide the meeting controls.
Wait, what am
To see the
Oh, I see. How do I hide the meeting controls?
hide floating meeting controls.
Oh, there we go. Okay, fantastic. Okay, and then slideshow, play from start. Okay, great. So now, okay, the real world and the virtual world, I think, are both happy. We're now living in the metaverse. Yeah, so, okay, so what are the motivations? So, when we do neuroscience, we're in it because we'd like to understand how the brain works or a neural circuit works, but, what does that really even mean, right? A more proximal version of that question might be, we'd like to understand how the connectivity and dynamics of the neural circuit give rise to behavior. And also learning's importance. We'd like to understand how neural activity and synaptic learning rules conspire to self-organize useful neural activity that observes behavior. So the field of machine learning has generated lots of neural networks that accomplish really interesting functions, functions that we know of no other way of doing in any other artificial system at the moment, right? The surprising thing is we know everything about their connectivity, their dynamics, their learning rule, their developmental experience, their training data, yet we don't have a meaningful understanding of how they learn and how they work. If we can't understand these systems, this should keep neuroscientists up at night as to how are we going to understand the brain. And so, and also actually, can we even go beyond current biological and artificial circuits and exploit novel physics to implement neuromorphic computations that even lowers power and higher speed? That's something we've started working on recently. So I think there are profound scientific questions involving how do we understand how nonlinear distributed neural circuits compute, even when we do have all the data. I don't think for a second that if we understand how these artificial neural networks work, we'll understand how the brain works. But the methods that we use to arrive at that understanding for distributed nonlinear circuits might prove useful in trying to arrive at similar or different understandings in the brain, right? So we outlined all of this in an opinion piece here. So we've actually been doing, in addition to neuroscience, we've been doing a lot of work on theories of deep learning and machine learning in general. And this is the Center for Mathematics, and especially this is, and applications. And in particular, this is the seminar on new technologies in mathematics. So actually, we've been using a lot of mathematics, these types of mathematics, to actually understand technologies. And so this is sort of summarizes our explorations. If you're interested, here's a review article.
This is supposed to be new technologies for mathematics, but it seems you're saying all mathematics for technology.
Yeah, sort of. Yeah, we want to be bi-directional. We don't want to. Yeah, the two-way streets. Actually, it does lead to some interesting new mathematics potentially as well, or the need for new mathematics. And so here's a review article where we kind of summarized the state of the field, our work and other people's work. Here's an older review article where we showed how ideas from statistical mechanics and condensed matter theory, namely replica theory, could be used in a unified way to understand learning, random matrices, random projections, compressed sensing, and so forth. So there's really a lot of room for an interplay between physics, math, and machine learning and neuroscience. And I think it's a really exciting kind of area to work in. Okay, I can't talk about all of that work, so I just chose kind of two talks that are related to the themes of an interplay between technology and mathematics relevant to the seminar. So the first is, what does the geometry of high-dimensional neural network error landscapes look like? And how can we systematically anneal or change them in order to aid optimization? And this will actually map to classical limits of certain quantum optimizers that can actually be built in the lab, and we'll use statistical mechanics to understand their performance. Then the next part is, how can we beat power law neural scaling? And I'll talk about what I mean by that. And this will actually connect more theory, more statistical mechanics with experiments in machine learning, and actually yield engineering performance improvements. Okay, so let's dive in. Okay, so my colleagues at Stanford in applied physics built a machine known as the Coherent Ising machine, which generates a set of interacting photons that can be used to solve complicated optimization problems. Here's a review article that we wrote recently on this. This is joint work with a fantastic graduate student, Atsushi Yamamura, and Hideo Mibuchi. Okay. The details of this particular machine are not that important. You can abstract it away in the classical limit as the following set of energy functions, right? So first of all, here's the energy function that we'd like to minimize. This is the famous spin glass energy function. And actually, a lot of combinatorial optimization problems of interest can be encoded in this energy function for a particular choice of the connectivity Jij. And the variables xi are plus or minus 1. So this is a combinatorial optimization problem. And we'd like to solve this problem for arbitrary Jijs. Okay? This is a hard problem to solve. So you might try to relax it. You could take these spins and make them real numbers and subject them to a spherical constraint. So this is the same optimization problem, but over a different domain. And this is the spectral relaxation, because the solution to this optimization problem, minimizing this energy, is just the principal eigenvector of J. You could, for example, ask, is the principal eigenvector of J at all related to the ground state of the corresponding Ising system? And in generally, they'll be different. Okay? What the coherent Ising machine does is it's a system where you have a parameter A that's related to the laser power that you're pumping into the system. And as you crank up A from negative values to positive values, the energy function on a single spin, which is now a real number, it's related to sort of the X quadrature part of the oscillation field of the photon, of an individual photon, and I indexes different photons. If the laser power is negative, then the single energy on a single photon is just has a single minimum, right? As A becomes positive, the single site term becomes the famous double well potential, right? And then you also have the quadratic interaction. So basically, as A becomes positive, the minimum of this problem interpolates between the spectral solution and the solution to the Ising system, right? So because when A is quite positive, the X's are forced to be near plus or minus constant. And then you also have the quadratic term that you're minimizing. Okay. So roughly, you can think of the Ising machine as interpolating between these two energy functions. And what we care about is, does this interpolation or annealing process ultimately lead to a good low energy solution of this original optimization problem that encodes a combinatorial problem of interest?
So
Okay.
is it, so it's known that max cut is NP hard.
Yeah.
And on the other hand, in the real case, this is just an eigenvalue problem. what is known about the classical computational complexity of this intermediate problem?
Nothing's known. Yeah, nothing is known. So we're going to do, we're going to analyze actually the case where the JIJs are random, and we're going to look at average case performance, not worst case performance. So yeah, so we're going to analyze the system when JIJ is just a random Gaussian IID matrix. This is known as the Sherrington-Kirkpatrick spin glass. It's a hard but not very difficult optimization problem. Okay, by hard I mean it's slow for simulated annealing, for example. Okay, and so the way the machine operates is you start from the origin. You start with the excess from the origin at a small value of the laser pump power. You increase the pump power by a small amount. You minimize the energy via gradient descent, and you repeat. So this is doing gradient descent on a slowly changing energy landscape. This so-called adiabatic evolution actually outperforms the spectral solution and comes close to the theoretically predicted Sherrington-Kirkpatrick ground state energy. So for example, the horizontal axis indicates different system sizes. If you take this principal eigenvector of J and round its elements and round them to plus or minus 1, the typical energy that you get is around this number, right? A little bit above minus 0.65. The actual Ising ground state energy is known to be down here, a little bit below minus 0.75. And these are what you get from different runs of the CIM as you increase the system size. And as you can see, the CIM comes much closer to the true ground state energy than does the spectral solution. So it's improving upon the spectral solution.
Say one more time. How do I have a keyboard?
Yeah, you literally
I
just crank up the power of a laser.
Keyboard was broken, but now I just do it out of I like it better.
Oh yeah,
Actually, so if
that's
I
the
eat food,
beautiful
my
thing
fingers
about
get
the
sticky.
machine. It's completely programmable. You can tune the JIs through a complicated set of optical devices, basically.
So is this a classical simulation?
This is a classical simulation. Yeah, this is all done on a computer. Yeah, these simulations were done on a digital computer. We're digitally simulating an analog system. but these analog systems actually exist. They're funded by a company called NTT. So very, very large versions of this consisting of thousands of photons exist in Japan.
Medical physics.
Oh, the dots are many runs of the CIM. You can do both for a given disorder realization, varying the disorder. This distribution is largely self-averaging, so you get sort of similar results either way. This could be the randomness of the disorder and compounded with the randomness of the initial condition. Yeah. The span of, as usual for in thermodynamics, as the system sizes become larger, the span becomes smaller. So this is 10 to the 4th. We don't. We're going to compute this analytically. I'll show you the results in a bit. Yeah. At finite n, we don't know how to compute this finite n gap. That's what I'm saying. But at infinite n, we have a formula for this. Okay, so the questions that we want to ask is what makes this possible? What is the shape of the energy landscape? How does it change with the laser pump power? And can we exploit our understanding of this changing geometry to determine an optimal annealing schedule for how you crank up the laser power as a function of time? In fact, we did that and we found an annealing schedule that worked. And I'm showing you the results of our theory essentially for what we get with the optimal annealing schedule. And so I'll explain how we got that. Okay, let me skip. Oh yeah, okay. So, so more specifically, what can we ask? So we'd like to understand the shape of the energy landscape and how it changes. So what we're going to ask is, in terms of the CIM energy E, this energy function, the radial distance from the origin, right, sum over I xi squared, the pump power A, where do the global minima of this energy function lie? Where do the most likely local minima lie? Where do the most likely saddle points of a given index lie? Where do the lowest energy saddle points of a given index lie? And given a critical point, either a minimum or a saddle, what is the distribution of this OPO, this is called optical parametric oscillators, quadrature xi? Like what do the distribution of the xi's look like at a minimum? And what is the eigenvalue spectrum of the Hessian at a critical point as a function of its index, energy, and radius? Okay. So before I go through the results, let me just give you the take-home message for the picture underlying this energy landscape at large A. So what you find is that the global minimum will occur at a very large radius in X space. So these two dimensions are a stand-in for n-dimensional X space. This vertical axis is the energy. The global minima lie at low energy and very large radius. Okay. There's a wall of typical local minima, and there'll be exponentially many of them that lie at a slightly higher energy and a slightly smaller radius. And then you get index 1 saddles where you have one negative curvature direction and all the correct other directions are positive, index 2 saddles, and so on and so forth. The higher in energy you go, the smaller the radius the saddles occur, and the higher their index, where the index is the fraction of negative curvature or the number of negative curvature directions. Okay, so this is the picture. And as you crank up the laser power, this picture unfolds like a peeling onion. And annealing works because you're always surfing the surface of this onion. Okay, that's a take-home message. Now let me justify it. All right. Okay. So what did we actually do? What we did is we used techniques from geometry, the Kac-Rice formula, and statistical mechanics, the replica method, and also supersymmetry, to count the number of critical points of a given energy and a given index. More precisely, we computed the logarithm of the number of critical points, and we averaged over the quench disorder. And so this gives us a so-called complexity of critical points at a given energy and intensive index. We computed it by computing this grand potential. We're averaging a log, so you can use a replica method. When you apply the Kac-Rice formula, you have to worry about the determinant of a certain random matrix. We can compute averages of the determinant of this random matrix by introducing fermionic integrals. So we have an integral over bosonic variables, the x's, and fermionic variables, related to the determinant of the Hessian. And they're related by a supersymmetry, okay? And there's also a replica symmetry in the replica method. And so the types of solutions that we find can either keep or break the replica symmetry or keep or break the supersymmetry. Okay. I realize that was a mouthful that may not make sense for anyone who's not an aficionado of these techniques, but really nothing about what I said matters. What really matters is that there's different classes of solutions that we find to the complexity, and they determine the shape of the landscape, which I'll now explain next. Okay, so here's the picture. Here's the results that justify this take-home message, okay? So this is at a large value of A. We did numerical simulations for a small system size, n equals 15, and we used Newton's method to exhaustively search for critical points of all index and their related energy and their radius. And this blue-green heat map shows what we found. It shows the density of critical points of all indexes, right? The black dots show the mean position of all critical points of a fixed index. The low index critical points, in fact, the minima of index 0 occur on average out here. So they're at low energy and large radius. So that's like this picture here. And as you go to higher and higher indexes, your critical points move up in energy and down in radius. So that's these circles here. Okay, what's the red curve? The red curve is what we predict from our analytic theory of replicated Kac-Rice formula. And you can see there's a nice match between the theory, which typically holds at n equals infinity, and the numerics, which we did at n equals 15. So we could exhaustively search for critical points. Okay, so this kind of justifies this picture, right? But this is for a large value of A. What happens is you slowly crank up A, the laser power. Okay. Oh, by the way, before we do that, we can also compute the shape of these minima in the sense that, if you find yourself at a typical local minimum, right, which is, remember, slightly higher in energy than that of the global minimum, as you crank up the laser power, this is the distribution of xi's at a typical local minimum. The blue is what we get from numerics. The orange is what we get from theory. And you can see there's a really nice match. And what's happening is you crank up the laser power, the spins or photon fields are committing to positive or negative values. At low laser power, they're not yet committed. That's sort of what you'd expect from a deepening double well potential intuitively. If you look at the Hessian around at the local minimum, this is the eigenvalue spectrum of the Hessian. The blue is numerics, the orange is theory. And you see that you have very, very flat minima in the sense that the Hessian eigenvalue spectrum has no gap away from the origin. There's always a finite density of minima near the origin. Sorry, there's a finite density of eigenvalues near the origin. So there's always some flat directions for a typical local minimum. What about the global minimum? Right, so that's a different state that's further down in energy and further out in radius. This is the same data, both theory and simulation for the global minimum. And as you can see, the global minimum commits more than the local minimum, but the Hessian eigenspectrum undergoes a phase transition where initially there's no gap, and then suddenly it develops a gap. So then what happens is the global minimum freezes in the sense that there's no flat directions. So if there were thermal noise, it couldn't explore the flat directions. It's frozen in a global minimum that has a restoring force in every possible direction. Okay. So this is an important phase transition in the global minimum that occurs as you crank up the laser power. Okay. So now with this data, we can construct a phase diagram for the energy landscape as you crank up the laser power. And it breaks into these phase boundaries as a function of the laser power. For a less than -2, -2 is the minimum eigenvalue or the minimal eigenvalue of J. For a less than -2, there's just a single global minimum at the origin, right? The Jij matrix can't pull you away from the origin. The single site potentials can't pull you away from the origin. Okay, for a bigger than -2 and less than -0.3, there's a so-called replica symmetry breaking in our theory that signals, what that really means physically, it signals that there's exponentially many local minima, but they all have very similar energy densities. So the energy per unit spin is the same for all of them. So the energy differences are sub-extensive in N, right? They're all marginally stable. By marginally stable, I mean that there's always these flat directions here. The Hessian eigenspectrum extends to 0. Okay, so you have this very flat landscape. So you have many, many minima all at the same energy level, and it's a very flat landscape. So you can move easily, but you can move between the minima, right? Okay, as you crank up A even further, there's a so-called supersymmetry breaking transition where you still have exponentially many local minima. Most local minima are marginally stable. The global minimum is also marginally stable. So that's like this region here, right? But there's now a range of energies for the local minima, right? So there's a whole bunch of local minima, and there's an energy range in which the global minimum to typical local minima live, right? Okay, and then there's this freezing transition that I talked about where the global minimum ceases to have flat directions. The eigenvalue spectrum develops a gap away from the origin. Okay, all right. So this understanding of the, okay, so now what are these simulations, okay? So for many, many problems, we computed the global minimum numerically at small system size. That's these black dots with error bars. And the green curve is our theoretical prediction for the global minimum of CIM energy. And you can see there's a nice match. Okay, the orange is the same for typical local minima. You can see the typical local minima and the global minima have the same energy up until this phase transition point, and then they separate. Okay, and then the blue curve is a typical critical point of any index. Okay, so here you see this separation in the landscape corresponding to this picture. Okay, so now here's the picture basically. So what happens in this range? Oh, and by the way, okay, so here's the red trajectory is the CIM energy that we get when we do adiabatic annealing, right? And the blue is the global minimum of the CIM energy. And you can see that adiabatic annealing follows the global minimum. It breaks below the energy barrier of the exponentially many local minima, right? And so just intuitively, why is that happening? It's because as you anneal the laser pump power, you're moving through this sequence of landscapes. Let's say you just started at large A and you had to just minimize over X starting near the origin. Then you'd have to traverse this very complicated landscape riddled with high index saddles and eventually low index saddles, and you'd get trapped somewhere around the typical local minima. But if instead you're annealing in this fashion, you never have to start from here. You start from here. You already get to the wall of typical local minima, which has the same energy as the global minimum. And then you surf the surface of this wall as it expands, and you end up in a very good place close in energy to that of the global minimum. So that's how the landscape annealing helps you from a geometric perspective. And using this, we can actually find the optimal annealing schedule and so forth. And that's what we use to get these results. But it's kind of straightforward based once you know the geometry to find the optimal annealing schedule. Yeah.
There's going to be some gap and some time it would take to get to slowly.
Yeah. So exactly. So this is sort of, so this curve is what you do if you do rapid annealing. This curve is what you do if you do slow annealing. And so the basic idea, and what this really tells you is that annealing beyond the freezing transition doesn't really help. And if you don't anneal beyond the freezing transition, the speed at which you do it doesn't really matter that much. But if you decide to blow past the freezing transition, anneal really fast, then you'll end up in a worse place, right? So we don't have a complete dynamic theory for that, but we see that the freezing transition beyond that is when the speed of annealing really matters in terms of where you end up in terms of the CIM energy. Yeah, you had a question?
That sounds like you sort of addressed this already, but in another way, what happens if you are starting a freezing and you search for minima starting with large form initialization?
Oh yeah, you end up at an energy that's close to like the typical local, somewhere between the typical local minimum and the global minimum, right? So you don't get all the way down here, right? This delta E is the difference in energy between the minimum that's found by adiabatic annealing and the global minimum at every value of A. Yeah.
When you say exponentially many, do you mean like
in N, yeah, in the number of spins.
You also have exponentially many.
I don't think so. No.
So
Yeah.
Do you have a unique
Well, okay. So I can't say if we have polynomially many global minima. Yeah, yeah. But I don't think we have exponentially many local minima. Yeah.
Did you try to study the depends of this time on N? I think the time.
We haven't done a careful study of that. What we did was we fixed a time scale, and we showed as we increase system size, we don't do worse. Yeah, but you're right. We haven't done a careful finite size scaling of the time with respect to system size. So whatever time scale we chose was slow enough for all system sizes present here. Yeah. Okay. Yeah, so we're using the usual Sherrington-Kirkpatrick scaling where the variance of the weights is 1/n. That's what allows the existence of a thermodynamic limit for the SK model. Yeah, so yeah, everything's contingent upon that. Yeah, but that's a sensible scaling to pick basically. Okay, so that, I liked this because the geometry provides some intuition as to why an optimization is possible when you anneal and not possible when you don't, right? I'll just advertise one more thing I started hanging out with my, actually started hanging out with people in my department who don't do neuroscience. And so that the AMO people, the atomic molecular optical people, they're doing really cool stuff these days. And so, for example, one of my colleagues was able to build a hot field associative memory out of a cavity QED system. And we helped them analyze the dynamics of the associative memory. And we showed that the natural dynamics that comes out of the cavity QED system is superior to zero temperature Glauber dynamics. And you can actually increase the memory capacity of this sort of quantum Hopfield model relative to the classical Hopfield model. I won't go into details on that, but if you're interested, it's all in this paper. So this was a fun kind of, we call it quantum neuromorphic computing, which I don't know if that's a good or a bad term, but yeah. Okay, so let's go. I wanted to keep the majority of the time for this beating this power law neural scaling, which is some work that we did very recently that just, it'll appear in NeurIPS at this upcoming NeurIPS. Okay, so what do I mean by all of this? So this is the team. This was actually an internship done by Ben Sorsher and Robert Garros working together at Meta with me and Ari Morkos and Shashank Shekhar. And this is the paper that will appear at NeurIPS. Okay, so here's the basic idea, okay? So people have observed in a whole bunch of settings these so-called neural scaling laws, where the error of a neural network trained to solve various problems tends to fall off as a power law with either the number of parameters in the model being trained, the number of training data points used to train the model, or the amount of compute used to train the model, okay? But the scaling exponents are small. So these power laws are very shallow. So this means that advancing AI through scaling alone is very expensive and completely unsustainable. I'll show you examples next. So for example, in a particular language modeling task, i.e. predict the next word with large transformers, a drop in the cross entropy loss of next word prediction from 3.4 nats, roughly think of it as 3.4 bits, but to 2.8 bits, requires 10 times the amount of training data. Another example for training large vision transformers, if you start with 1 billion training points, you'll get a certain error. But if you add 2 billion data points, you'll drop your error only by 2 to 3% on ImageNet. So 2 billion data points, an additional 2 billion data points starting from 1 billion, buys you 2 to 3%. And typically scaling laws are like this. Okay, so let me again just give you the key ideas and take-home messages before I dive into the results. So the key idea is that slow power law scaling of error with data set size, that's the thing that we're going to focus on in this talk, indicates that the training examples are highly redundant. New examples don't buy you that much. Therefore, we should be able to prune data sets to identify sparse or small subsets of non-redundant examples. And if we were to plot error as a function of pruned non-redundant data set size, we might be able to beat power law scaling. That's the hope. And so what we show is we show analytically that we can do this in theory for perceptron learning in a student-teacher setting. And there we can at least achieve exponential scaling. And then we show in practice how to beat power law scaling in vision tasks on benchmark vision tasks. For example, ResNets trained on SVHN, CFAR10, and ImageNet, and vision transformers pre-trained on ImageNet and fine-tuned on CFAR10. And the pruning algorithm matters. So we did a benchmarking study of 8 different pruning algorithms based on different pruning metrics. And we actually developed a new metric that's cheap, scalable, and easy to compute given a pre-trained foundation model. I'll talk about what I mean by that. And it doesn't actually require labels to compute, so it can be done in a self-supervised fashion. And our metric allows us to train on about 75% of ImageNet without suffering any drop in accuracy whatsoever. Yeah. So real data can be IID, but still be redundant, right? Because let's say there's a high probability density in a localized region. Once you get one example from that localized region and the right answer, you're done. Any more examples from that same localized region don't give you any information about the function you want to compute. Okay. Okay, so this work was actually motivated by some earlier work that we did with Manshij and Carolina, where we just tried a particular data pruning strategy that we came up with, okay? So here's the basic strategy, okay? So you have a big data set and you wanna figure out which data points are important. Okay, well, one strategy is train on all the examples in your data set, say in this case, CFAR 10, for a small number of epochs, say 20 epochs or something. Now, for each example now has a distance to the decision boundary, right? Compute each example's distance to the decision boundary in the output probability space, okay? The so-called L-tune score. Examples with a small distance to the decision boundary, quote unquote, haven't been learned, at least in 20 epochs. We may think of them as quote unquote hard examples, right? On the other hand, examples that are very far from the decision boundary and of course correctly classified have been learned very quickly in 20 epochs. So they're by definition easy examples, okay? We can denoise the system by averaging these scores over, so we can score the examples by this L-tune score, distance to decision boundary. We can average the scores by training over a few short runs, maybe 10 or so. And then we can prune the data by retaining only a fraction F of the hardest examples. The gut intuition is the easy examples are easy, why devote more training time to them? So then we keep only the hard examples, and then we throw away this probe network and we start from scratch and train on the smaller, pruned, hard data set, okay? So how many examples can you prune in this way before suffering any accuracy loss? On CFAR 10, we could go down to 50% and have no accuracy loss. On CFAR 100, we could go, this doesn't seem right. We could go, this is the one minus that. So we could go to 75%. We could prune away 25% of the data and keep 75% of the data and not suffer any accuracy loss. Okay, and these are curves of accuracy as a function of the amount of data that we pruned. This is, this blue curve is our method. This red curve is if you just pick stuff randomly. That's the correct baseline, right? Does your method do better than just randomly picking examples? And it does do quite a lot better, okay? So that was the initial motivating work for the work I want to talk about. Okay, so, but this work raises a whole bunch of questions, right? Why does data pruning in this fashion even work? Why is keeping the hardest examples the right approach, or is it? Can we develop a mathematical theory of data pruning? How does performance scale with pruned data set size? And does data pruning even scale to ImageNet? This paper only did small experiments, CFAR 10, CFAR 100. Can it work in ImageNet, or do we need new metrics there? So these are the questions we kind of set out to ask. Okay, so we started with the theory. We just wanted to understand data pruning in a simple setting where we could analytically compute the test error, right? So we worked with this tried and tested teacher-student scenario for perceptron learning. So basically in this scenario, we define the data generating process as follows. You have a teacher perceptron whose weight vector in n-dimensional space is given by this vector. So the decision boundary is the n-1 dimensional hyperplane perpendicular to the weight vector. We pick this teacher randomly. We pick a bunch of examples from an isotropic distribution in an IID manner, right? So these are our random examples. Those on this side of the decision boundary are the plus examples. Those on this side of the decision boundary are the minus examples. Okay, so this is how we generate the training data. So the teacher decides the labels, and the inputs are otherwise random. Okay? So the pruning strategy is mirroring the previous paper. We train a probe student network that may, for a very short amount of time, so it may not align quite well with the teacher, right? And the probe student has its own decision boundary that we have access to. Remember, we never have access to the teacher directly. We can compute the margin or the distance of each data point to the decision boundary of the student, and the large margin examples are the easy ones, the small margin examples, the hard ones. And we keep the hardest data with the smallest margins with respect to the decision boundary of JProbe. Okay, so that's our pruning strategy. Then we start from scratch. So now we have a non-Gaussian distribution of training data because we truncated the distribution along the probe direction. So we analytically compute the test error of a max margin learner on the non-Gaussian prune data trained from scratch. So, okay. We operate in the usual high dimensional statistics limit where the number of parameters, n, and the number of data points, p, both go to infinity, but the ratio of data points to parameters, i.e. the amount, the intensive amount of data, is held to be order 1, right? And f is the fraction of examples that we keep. So if the total data set size is alpha total, the pruned data set size is f times alpha total. And we're interested in performance as a function of the amount of training data we actually give to our algorithm, which is the pruned data set size. Okay. All right. Any questions on the framework? Yeah.
Otherwise, you might worry that disregard some of the easier examples.
Yeah, we'll talk about that. Yeah, when we discuss optimal pruning strategies. Yeah, that's a good question, and I'll discuss the intuition in a few slides. Oh, the threshold is chosen by the fraction f that we keep. So we just we score the examples by the distance to the margin, and we keep the fraction f that have the smallest distance to the margin. Right. Yeah. Okay. Okay, so here are the important parameters of the problem. Okay. There's the angle theta between the teacher and the probe, right? There's z, the projection of the data x onto the probe. There's p of z, which is the distribution of the pruned data along the z coordinate. That's non-Gaussian, right? But the data is otherwise Gaussian in all the other directions perpendicular to J probe. There's kappa, which is the margin of the student network. So we train a final student network. That's the one we train from scratch. And it has a certain margin, kappa. And alpha is the ratio of examples to parameters. Okay. We're going to maximize kappa while still getting all the training data correct. So we're finding the max margin learner eventually. Okay, so there are certain quantities which concentrate in the high dimensional statistics limit. Rho, which is the cosine angle between the student and the probe, right? So this between the student and the probe. And R, which is the cosine angle between the student and the teacher. The generalization error gets smaller as the student gets closer to the teacher. So actually the test error is the inverse cosine of R, is proportional to the inverse cosine of R. So R is the order parameter that we care about. Okay, it turns out that what replica theory allows us to do, we apply replica theory to the setup, is allows us to find self-consistent equations relating these self-averaging or concentrating order parameters R and rho to the parameters of the problem, theta, P of z, kappa, and alpha. And these are the equations. You don't need to parse the equations. I'm just showing you that there's actually something solid behind what I'm about to tell you. Okay. So then what this allows us to do is it allows us to analytically compute the test error as a function, as a joint function of alpha total and f. Okay. So that's what's plotted here. But we plot the test error as a function of alpha prune, right? So for any given alpha prune, there's many ways to get to a certain alpha prune. For example, you could have f equals 1 and you just keep all the data, right? And that's this curve. So that's like no pruning at all. And it's well known that this exhibits power law scaling with an exponent of -1. Okay. Or you could start with a larger alpha total and do more aggressive pruning to get the same alpha prune. And that's going down here, right? Okay, so what you're seeing is this family of curves, and you see that if you follow the strategy of starting with more data, but pruning more aggressively at fixed prune data set size, you do much better in terms of test error. And if in this joint alpha total F space, you find the Pareto optimal point of minimum test error at fixed alpha prune, you find a lower envelope of these curves that actually exhibits exponential scaling, not power law scaling. So you can achieve exponential scaling in this fashion. However, if you don't change your pruning strategy, i.e. change F with the total amount of data you have, then eventually you'll do better than no pruning, but you'll eventually settle into a similar power law, right? So you really need this Pareto-optimal strategy to achieve exponential scaling, at least in this setting. Okay, so that's what these words kind of, sorry, very important. This is assuming you have access to a perfect pruning metric. Remember where J probe equals the teacher. So I'm basically pruning with respect of the examples with respect to their margin on the teacher's decision boundary. I'll talk about what happens when theta is not equal to 0. So you have an imperfect pruning metric in a couple of slides. Okay. But notice over here, pruning actually does worse. Okay. This is when you keep the hardest examples. It turns out keeping the hardest examples is not the optimal strategy if you don't have much data to begin with. And what we found, what we predicted from our theory is that if you have a lot of data to begin with, keeping the hard examples is better. If you don't have much data to begin with, keeping the easy examples is actually better. Okay, so this is a qualitative prediction derived analytically from our theory. Does this qualitative prediction hold in much more general settings far beyond the regime of applicability of the analytic formulas underlying our theory? And remarkably, it does. We did the same experiment for a ResNet 18 on CFAR 10, and we found that if we start with a very large data set, we do better if we keep the hard examples, but if we start with a very small data set, we do better if we keep the easy examples. So what does this look like geometrically? If you don't have that many examples to begin with, you want to keep examples that are near the poles that give you a strong signal about the teacher direction, given that you don't have many examples to communicate to the student. On the other hand, if you have lots of examples, you want to keep the hardest examples, which will concentrate near the teacher's decision boundary. And because you have lots of examples, you'll be able to fine tune the student's decision boundary to better match the teacher's decision boundary. Right, so that's kind of the picture underlying the results. Okay. Let's see. Oh, sorry. So, no. So remember the procedure is you train a probe. You just train a probe, right? And then you just once and for all compute the distance of each example to the probe's decision boundary, right? And the question is, do you keep the ones with the smallest margin or the largest margin? Or that's the decision. You make that decision one shot, and then you start from scratch and train a pruned teacher. The basic motivation behind all this is I want to eventually create what I call so-called foundation data sets that are carefully curated data sets that I can then disseminate to the public. And they can train all various models on these foundation data sets. That's why we're focusing on one-shot pruning and not active learning, where you keep changing what you do after every example. I'll talk about that at the end. Yeah, the power law is only set in when you have lots of data. Yeah, power laws are always on the right-hand tail, right? We can't guarantee anything about the learning curves when, by the way, sorry. The solid curves are theory, the dots are numerical simulations, and there's a match between theory and simulation. So we can analytically compute the learning curves for small alpha. They just don't look like a power law. But whenever I say power law, I'm always talking about the right-hand tail. Yeah.
So you said you do the one-shot pruning, then you just make the signal fraction.
Yeah.
But is there a useful strategy timing as well? Like say these examples first to lock in the
yeah. So that.
Yeah.
Yeah, that gets into issues of curriculum design and more sophisticated strategies. We haven't explored any of that. So for example, you could imagine a concept called foundation curricula, where you not only provide one data set to the public that's a really good data set, you provide a data set and a policy for introducing examples one by one. Yeah, it's a completely open problem. We haven't looked at it. I suspect that'll be actually very important because That's what we do for our kids, right? I mean,
You're supporting now acceleration for models.
I'm not
challenge the models, give them
I'm not supporting the California curriculum framework. Yeah. Oh, I'm on Zoom. Okay, sorry. Go ahead.
So just to be clear, so the parental frontier is the envelope of the
Yeah, that's right.
questions. But so in the end, how do you beat the follow-up? Like you have to actually train, you have to.
I'm just saying there's a sequence of data sets for which performance will scale exponentially with data set size. So basically what this theory, at least for the perceptron, tells you is if you have a large data set, prune more aggressively, and you'll do better than if you had a small data set and you prune less aggressively, right?
Yeah, I'm just wondering, like in practice, right? If you want to get a really low exponential test loss, then
Yeah.
you could construct this sequence of.
Yeah. So in practice, what you do is you have a data set to begin with, and you try to crank F down as small as possible until you don't see any, until you start like increasing the error. So in practice, you're stuck with a fixed data set, right? Unless you want to collect more. This could tell you the benefit of collecting more and pruning more aggressively, right? So it might guide policies in data collection versus pruning. But yeah. Yeah, Henry?
Can we do think of something like data set distillation where now you're taking some existing images and trying to.
Yeah, we didn't play around with data distillation where there are basically no rules. You can come up with whatever data you want, even artificial data, and train on. Yeah.
Might be even unnatural.
Yeah. We didn't. Yeah, we looked at some of those papers. We haven't played around with the theory of that or anything. I think that's another open problem as well. Yeah.
Whether the data set is invariant.
Yeah, we've done that. We've done transfer studies where we prune using one architecture, and we use the prune data set to train using another architecture. We also do a benchmarking study of 8 different pruning metrics and compute the Pearson correlation coefficient between them. And I'll show that slide at the end. Yeah.
And remember that we don't have a hard cutoff. So
Okay. I think probably in 10 minutes I can go through. Things are going to get much more practical soon when we start doing a real world, quote unquote, real world experiments where the real world is ImageNet. At least it's not CFAR 10 or MNIST, heaven forbid. Okay, so by the way, these statistical mechanics methods are very powerful. I'll just advertise one paper that I'm particularly like. That was done with Madhu Advani, who actually used to be who was in my lab and then did a postdoc here at Harvard. We were actually also able to find the optimal loss function and regularizer for high dimensional regression with non-Gaussian signal and noise. And so that's in this paper. There's some overlap between the mathematical techniques of this paper, in the paper I'm discussing in this paper, because of the non-Gaussianity of the data distribution. Let me skip that. Okay, the quality of a pruning metric matters. Remember, I was discussing when theta equals 0, so we're pruning according to the teacher. What happens if we have an imperfect probe metric? So the probe has some non-zero angle with the teacher. We can work out the theory analytically. Those are the solid curves. The dots are simulations, they match. The take-home message is the closer the probe is to the teacher, the longer you can delay the transition from exponential to power law scaling. But eventually you're going to hit power law scaling, and there'll be a minimum fraction below which pruning will not help you, okay? And that minimum fraction increases the larger the angle between the probe and the student, okay? So that's the basic take-home message. So pruning can still help, but only up to a certain point if you have an imperfect probe. Okay, the intuition behind all of this is we can compute the information gain per example. So for example, so what is the information gain? You can look at the entropy of the distribution of perceptrons that are consistent with your training data, okay? As you add more examples, that entropy will go down. The rate of decrease of that entropy is the information gain, okay? And what happens is if you do random pruning, this black line, the information gain per example is decreasing with the number of examples. This is a measure of redundancy. With each new example, you have diminishing returns in the information that you gain. If you do this aggressive pruning strategy, asymptotically, as you get more and more initial data and prune more aggressively, the information gain asymptotes to a finite constant, okay? And so basically each new example is giving you a finite amount of information, which explains the exponential decay of the tester with pruned data set size. Okay. All right, let's get practical, okay? So these are experiments that were done at Meta that of course require some amount of compute, not crazy amounts of compute, but some amounts of compute. And this is experiment. So this is the perceptron in the teacher-student setting. This is what you've seen before. This is a ResNet 18 on SVHN. This is the usual power laws that you see if you keep all the data, 100% of the data. And these power laws are consistent. The power laws that we find are consistent with power laws reported previously in the literature. But if you do this aggressive pruning strategy, where for larger initial data set size, you prune more aggressively, you definitely beat the power law. And you start to see the beginnings of better than power law scaling. Now, we can't get down here because we're starting with a limited data set size to begin with. The theory predicts that if we had an even larger data set to begin with and prune more aggressively, we might be able to get even lower in this regime. Okay. Yeah, so what we're doing now at Meta is we're actually, does somebody have a charger? This recent one. Oh wait, I have a charger. Yeah, so what we're doing is we just got through legal, and Ari Marcus did this. We just got through legal to download the Lion data set on our servers at Meta. And this has 400 million, depending on which subset of the data, it has 400 million image text captions. And if you take a larger subset, you can get to 2 billion. And so we're trying it there now, right? Oops, sorry. Perfect.
Ever since language models should be similar?
So we just did an experiment on pruning language models. This is a transformer trained on Wikipedia, and we can drop to 50% of the training data without suffering any drop in perplexity. I'm really curious about what the hard and easy examples look like in the language space. A pruning metric that's going to appear on the final slides. Yeah. Okay. So in any case, I think pruning exhibits promise, okay? Now, we also do it in transfer learning. So you can take a vision transformer pre-trained on all of ImageNet 21K and fine-tuned on different pruned subsets of CFAR10. And this is the number of fine-tuning examples. And we again beat power law scaling here as well. So these power laws are not an immutable law of nature in the context of machine learning. They can be changed if you do different, more intelligent things like training on curated subsets of data rather than random data. Okay, let's see. Okay, there's a bunch of other work on pruning. It'll take me some time to go through the details, but let me just skip all of this. There's just a bunch of different scores that you can use to prune. They're all very interesting. We benchmarked all of them, and ours did the best. I mean, I'm trying to go through really fast the take-home messages. And we actually developed a new method for, so some of these pruning metrics are very compute intensive. So we tried to develop a cheap pruning metric. And this cheap pruning metric is this light blue curve. This is the fraction of data kept on ImageNet, and this is the performance. And our light blue curve does really well. It does much better than much more compute intensive metrics. So what is our light blue curve? Let me explain that, and that will answer your question, Michael. So we followed this intuition of we want to train on non-redundant data. So how do we find the non-redundant data? What we can do is we can start with a pre-trained foundation model that gives us a nice representation space for images. And we can feed ImageNet images into that pre-trained foundation model and get their representations in the final layer of the foundation model. And we can just cluster those representations, right? Well, for example, we could do it in a supervised way where if we know the class labels, we can compute class conditional centroids for each class in this embedding space. And then we can compute the distance of each data point to its centroid, and that's our score. The hardest, the quote unquote hardest ones are by definition the ones that are furthest from the cluster centroid. They should be in some sense idiosyncratic outlier data points. So maybe we only train on the idiosyncratic outlier data points. But of course, we modulate the fraction that we keep. So we could include some of the ones close to the cluster centroid as well. Okay, that's if we know the class conditional centroids. So that's if we know the labels. What if we're in a setting where we just have unlabeled data? What could we do? We could do the exact same thing, except we can use k-means to clustering to determine the centroids, right? So right now, we're working on implementing k-means clustering of billions of data points, right? But this is what these tech companies are really good at, and nearest neighbors and things like that. Okay, anyways, so the basic idea is use k-means clustering to cluster the unlabeled images using a pre-trained foundation model, and then compute scores by distance to the center of each example to the centroid. Okay, and that's our metric. And so that's what we call self-supervised prototypes, and that's this dark blue curve here. So you can see you can get to 80% of ImageNet, get down to 80% of ImageNet with essentially no loss in performance. You start to see a loss of around 70%, so we're guessing around 75%. You're kind of within the standard deviation that you get across training runs. And I believe this is the state of the art for how much you can prune ImageNet at the moment. Okay, we computed the Pearson correlation coefficient between all of these metrics. There are some metrics that are somewhat different from the rest. Now you might ask, what do the data look like, right? So we took just 3 ImageNet classes, class 100, 200, 300, just so we're not cherry picking. And these are the easiest examples according to a self-supervised metric. So these are the examples that are closest to their cluster centroid. These are the hardest examples. Intuitively, you can see that the quote unquote easy examples are all very looking similar images of swans, right? Black swans in this case. The hard examples are all very idiosyncratic images of swans, right? So, once you get this image, you don't really need this image in your data set, right? So that's the intuition. The same thing holds for class 200, which happens to be Tibetan Terrier. These are all stereotypical images of Tibetan Terriers. The hard ones are all idiosyncratic images. And then here's the tiger beetle class. These are all stereotypical. The hard ones are idiosyncratic. There's even this weird cartoon of a tiger beetle, which, is a tiger beetle according to ImageNet. So this, our metric is intuitively picking up on the idiosyncratic examples and suggests that if you train on the idiosyncratic examples, you'll do well, at least on ImageNet. Okay. Yeah, I'm a little bit over. So I'll skip the summary. Let me just highlight the philosophy of where we might go forward. So our current practice of ML, collect and train on large random data sets, is highly inefficient and unsustainable due to slow power law scaling with increasing data set size. The reason is in large random data sets, most data is redundant. Perhaps we should invest in the search for and computation of good data pruning metrics that can identify so-called foundation data sets, which are what I define as high quality, non-redundant, small data sets capable of accurately training many, many models. The potential computational cost of finding foundation data sets can be amortized across the gains in training many downstream models. And this is in direct analogy to how the computational cost of training foundation models can be amortized across the efficiency gains in fine-tuning them across many tasks. And so, the future lies in self-supervised learning where you get these huge data sets. And the question is, do we really need all of these data sets? So the next thing we're working on is pruning for self-supervised learning at the moment. Can we carve and disseminate much smaller foundation data sets out? All right, I'll stop here. Thanks.
So we have some time for questions.
Yeah. So for
Yeah.
Exponential of interest, but the exponent.
Yeah, I don't think we've actually worked out an analytic expression for the Pareto frontier. We have hints that it might actually be super exponential. We have to do some asymptotics to really sort that out, but it's at least exponential. It's at least faster than it's could be faster than exponential. It's not slower than exponential. Yeah.
Sure, I think this is very nice, like show this data pruning on classification problem. I'm just wondering for people who are interested in material science, for example, like it's more like on the regression. So like what kind of method can we apply this, or you have to change a lot of things to do this data pruning for regression?
Oh, I see. It's an interesting question. So you can't use margin with respect to the decision boundary anymore, but you could, for example, just compute mean squared error at early points in training. That's a possibility. It's an interesting question, but that is a theory that we can work out, because we've also worked on the replica theory for high dimensional regression with non-Gaussian data. So we could potentially plug into that theory and work that out and figure out what a good pruning strategy there would be. Yeah, that's a good rotation project. Yeah. 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 Oh yeah, we just done like the first experiments on pruning. OPT, it's a meta language model. It's one of Meta's language models. Literally, we did the first experiment last week, and I just saw the data like a couple of days ago, and so all I know is that if you train a language model, autoregressive language model on Wikipedia text, and you throw away up to 50% of the examples, you don't get any drop in the perplexity. We haven't done, what you really want to do is test on downstream tasks that people care about and so forth. So there's lots of work to do there, but it shows that data pruning could be promising for language. Yeah.
Fascinating to know what the easy and hard is.
Exactly. Yeah. I'd love to know that. So I'm talking to the research engineer, as soon as I get back, and there's lots to explore there. Yeah.
I'm wondering whether you look at data from models and sequences where experts they have a sense about what could be hard, what could be easy with different metrics like homology, identities. And I don't think we have sort of sophisticated analysis based on pruning, but there is some work meta AI, as you may know, ESM1B and ESM4. I mean, they suggest that the bigger the better. So I'm wondering whether you thought about
the bigger in data set size. So it's always the bigger the data set size, the better. The question is how much of that larger data set is redundant, right? That's the question. And we don't know. I mean, we just don't know the answer for sequences. I haven't talked to the ESM folk actually, but that would be interesting. It is interesting actually in scientific domains that we might care about a little bit more. What is a notion of an easy and a hard data point? And by the way, I don't want to insinuate that the definition of an easy and hard data point is at all settled. Like it's not really clear how to define them. We define some metrics, and I'm just attaching the labels easy and hard for us to be able to talk about it. But these aren't like foundation definitions. Boaz?
So this intuitively, if you have the data that you're training on, you might be also able to have the model size. You need to memorize less, or you've told the model that someone needs to memorize less. Did you try to do that to see if?
So that's like the.
If you want to have the data, can you also reduce the model size by half without losing? Or?
Yeah, we that's a really good question. We haven't tried that, and that's like the chinchilla philosophy, right?
Yes.
Is you jointly scale model size and data set size, and in this 2-parameter space, you find an period optimal operating point, and you find that you just scale both together.
Yeah,
we have unfortunately a 3-dimensional.
They say if you double the model size, you should double the amount of data. If you half the amount of data by pruning, maybe you also half the model size and you won't lose anything.
Yeah, we could explore that actually. Yeah, it's just now you have a 3-dimensional family of original data set size, model size, and the fraction you prune, and you want to find a period optimal operating point in this 3-dimensional space. conditioned on maybe total compute, right?
So, I mean, one natural question would be, suppose you are in a setting where you could say prune to 50% data without losing anything.
Yeah.
Could you, and these are models that somehow are very easy to scale by a factor of half. Could you half the model and not lose anything as well? Could you somehow get for free by data pruning, also get model pruning?
Yeah, that's a great question. We can try it. I'll put that into the queue of experiments, which is quite long at the moment. But that's a great suggestion. Yeah, maybe in the back, you've been waiting.
You mentioned alternative tasks that the same data set can be used.
Right.
It's not clear to me how this steps those, because both in the self-supervised and in the supervised settings, like they're very much pretty for those.
Yeah. So I'm talking about the next step, which is pruning for self-supervised learning. Can you, like, for example, with, do you really need this 750 billion tokens to get an accurate representation of text for next word prediction? Maybe not, right? And then if you don't need that many tokens for next word prediction, and you get a pretty good next word predictor system, can you use that for downstream language tasks without suffering? That's an open question. We don't know.
Sorry, I'm specifically talking about the idea of reusing these.
Yeah.
Releasing the foundation data set.
Yeah.
What's the thing you can derive from the foundation data set that is different from the model that's trained points?
Well, you would get a non-redundant set of sentences in English, for example. Yeah. So it's interesting in and of itself, and yeah, because if you look at we looked at some of the there's a lot of sentences that are repeated in Wikipedia, especially the short sentences, right? So it's not clear that we need all of those sentences. Yeah.
Do you have a sense or proposal for data generation? Because, in some sense, if we are not compute limited, but data limited,
yeah.
right? There's all that data, and by pruning, you're just gonna do as that much data, just saving some compute. But for new data generation, can you maybe use the non-redundant data and feed it to some generative model? Not sure. Some thoughts on this kind.
Yeah, it might. So short answer is no. I haven't really thought deeply about that. But what I would love to understand is what are the special, right? By fiat, it's points that are far away from cluster centroids. But is that the best thing to do? I don't know, right? We're actually working on a very simple mathematical theory for pruning in the self-supervised learning setting, and we're going to test that strategy and see if we can find better strategies analytically. But I think that's an open problem. We're working on it right now. Yeah.
Question from the audience.
Oh, yeah.
Are there computation time guarantees for how long it takes to do?
In short, no. I mean, what we do is in all the empirical work, when we prune a data set, we train for the same number of epochs of the prune data set as we do on the larger data set, which means we train for fewer iterations. So it's definitely faster to train on a prune data set than an unpruned data set. So there's that. I suppose in the perceptron learning theory, yeah, there are theorems about how we just find the global minimizer analytically, but when we numerically implement our perceptron learning, we don't see any slowness in training on the pruned data set relative to the unpruned data set of the same size. Yeah.
So can you completely off, but is there a connection between this redundancy and also symmetry? So in the sense that when you transmission symmetry, they're pretty much the same thing, right? Or maybe an Ising model, for example, you have these symmetries, and
yeah,
would be there connection there? Or?
Yeah, it depends. I mean, if you're if your network builds in the symmetry, then different data points under the orbit of that symmetry are redundant. But if you don't build in the symmetry into the function that you're training, then you'll need exemplars that are on orbits of the symmetry group, or different exemplars that are related to each other by the symmetry group.
So you're saying we can test that by applying symmetry on a network and then see if the pruning groups can improve it?
Potentially, yeah. I mean, that's the whole idea behind convolutional networks, where you copy the filter across space, right? So that if you learn something in one part of space, it's easier to learn the same thing in another part of space. So whether redundancy relates to symmetry, I think it really depends on the architecture.
So you characterize the pruning by one number, typically the fraction, but you could have said things like, let's prune a big cluster.
Yeah. So it's a very good point. We explored a very limited space of strategies over which we computed a Pareto optimal point. We actually asked, so we actually solved a more general problem analytically here, which is we had an arbitrary data distribution along Z. So you could ask at a fixed alpha total, what is the optimal distribution rho of Z? And we solved that problem. The answer is, for very small alpha total, rho of Z should be a delta function as far out as possible. So i.e. you're providing a very strong signal about the teacher's weights. But as you increase alpha total, the delta function comes in towards the origin. So that's actually the optimal data distribution. It's always a delta function in Z, yeah. Now, the problem is that's a too big of a class of strategies because you're stuck with a fixed data set to begin with. So you may not be able to realize the optimal data distribution given a fixed data set. But it does suggest an intermediate set of strategies where you prune margins between a certain lower range and a higher range, and you move that range in. And we've played with that. And what happens is, we haven't played with that, but what we did do is we found the lower envelope of keeping easy and hard examples, and it pushes everything down a little bit. Basically. Yeah, you had a question back there?
Yeah, here's how like the data can help the model can help the data with the zero examples.
Yeah.
And it shows that like maybe for us it looks the same, but like
yeah.
because you think it's similar.
Yeah.
And then you only looked at accuracy.
Yeah. It's a good question. We didn't specifically look at adversarial examples, but we looked at two other metrics. One is fairness and one is OOD generalization. So we did various OOD tests on the data trained from models trained on prune data versus not. And we didn't find any differences in the OOD generalization metrics. It didn't get worse, it didn't get better. Fairness, we looked at class conditional accuracy across all the ImageNet classes and asked, are there specific classes that do worse? And we didn't find a very big, so performance of a model trained on prune data for a specific class was strongly correlated to model performance in that class for a model trained on unpruned data. So those are the two things that we looked at. But I agree, adversarial examples would be very interesting. I'd be surprised if there were differences, but it's an empirically open question. Yeah, sure. Yeah. That's right. Oh. Yeah. I'm not sure. The double descent phenomenon, we were just talking about this today with Michael. It's not very fun. The peak in the double descent is not very fundamental. Like whenever you see that peak, that means you're doing something suboptimal, right? So I'm not sure that it's related, right? We're always doing the optimal thing, which is finding the maximum margin classifier for the perceptron analytically. And then, for deep networks, who knows what we're doing? We're just doing stuff and measuring performance. So I don't think it's related to that. or at least I don't see any obvious connection. Yeah. Right.
This can be another question, but is there any like interference between like something exists like you separate into particular class turned out smarter? Those that really just focus too much on that. And also especially
Yeah. 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 So in the ImageNet experiments, it was also important to balance the classes. So for example, we did a balanced pruning where we kept a fraction of the examples, but we did this in a class conditional way where we'd equalize the number of examples from each class. So that was helpful for performance. Yeah. So an open question is how to do class balancing when you don't have labels. There, I think the answer is you do k-means clustering, but with a very large value of k. And that worked actually for ImageNet. Actually, we varied the value of k. So ImageNet has 1,000 classes. We could go k down to 200 and up to, I believe it was around 3,000, 4,000. And the results were robust to that choice of k. So basically, if you do the supervised prototypes, you have to class, or if you do the supervised pruning metrics, you have to class balance. If you do the unsupervised pruning metrics, you don't have to. Yeah.
That also allows people to continue learning from the stream.
Yeah.
Then the question becomes, want to learn things like
yeah. 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 Continual learning, I think, I mean, there's no notion of pruning there, right? You're just getting examples one at a time and you do what you want with each example. Yeah, yeah. So yeah, you get to choose what your update is for each example and your current model. Yeah. Yeah, that's a different setting. I'm not sure if what we say in this setting would or would not be helpful in that setting. But this is all connected to active learning as well, and so forth. So I think there's overlap there, but the details need to be worked out carefully. Yeah. Yeah, Blas.
So I think this strategy is very, in vision settings, you have basically the Bayesian optimal is 0% error, and there is a deterministic label. But if you have the noise, then pruning might be in some sense, pruning the hardest samples might be the wrong thing to do.
Yeah,
because
yeah.
if you had some fraction of samples where the label is simply noise, then they would be the hardest.
Yeah,
you
yeah,
don't
yeah.
want to increase that
Exactly. So we observed this in the deep learning and the data at the first paper. We actually showed that the hardest examples were actually mislabeled examples.
Yes.
And so then you want to use a bigger set of pruning strategies where you keep margins within a certain range, where the upper range is close to the maximum, but not the maximal. And so you have a 2-parameter family of strategies, right? And I suspect that for the perceptron theory, that 2-parameter family of strategies would do better than our 1-parameter family of strategies.
That can converge to the delta function.
That could converge to the delta function, except you're always stuck with the finite sample that you start with.
The bigger, I mean, as the data set goes to infinity.
Yeah, yeah. Then you can get the delta function. Exactly. Yeah.
And probably language models where you also have amount of noise or uncertainty might be too.
Yeah, definitely. Yeah. We observe even for CFAR 10, CFAR 100, like the 2-parameter does slightly better. I mean, there's very few mislabeled examples in this, so it doesn't really hurt you that much. And then there's benign overfitting also, that interacts with it as well. So.
Okay. Well, why don't we? Thanks for that.
Thanks. Yeah.
We will be having the next seminar and we're going to publish the guide they are from Google.
Oh, yeah.
Solving quantitative reasoning problems with language
Let's see. Oh, lots of stuff in the chat.